Go ahead.
Yeah, okay. Hello, everyone. So today I'm going to tell you about this paper, tensor field networks, and in general, mention about mm, series of works by this group, because not only they propose this method, this particular method for 3D point clouds, but they also consider general approach like group convolution and how you can use this one. Uh, so the story goes back to the simple convolution uh, networks, right? So the idea there is that, let me just yeah, briefly introduce that to you. Let's go here. So the idea with the simple convolutional neural networks is that you impose some constraints on your neural network, or you basically try to help that to learn some translations or invariances in your data set. Another approach that was before convolutional neural networks is that you can just augment your data. So imagine that you have mixed, uh, right, a set of digits, and instead of just putting them in your neural network and predicting the output, you can just uh, increase the data set and add more examples of rotated digits, shifted digits, etc. So by doing that, you also teach your neural network to learn symmetries, but because they are in the data set implicitly, right? Uh, uh, and so convolutional neural network is kind of a way to go around this these translations or some rotations that you make to train your neural network better, and it goes uh, directly in the constraints of neural network. So, in general, we can think about the um, any translations that we can use or some group actions, right? So at this point, it is important to uh, understand what is equivariance, right? So suppose that you have, uh, and that's actually not a good action here. So yeah, for that, would go to the blocks that I also recommended. Um, okay, yeah. So suppose that you have, uh, let's see, yes. So suppose that you have uh, your neural network, which is some, for example, encoder, which is some function, right? So, and you have some group action on your data. So equivariance says that you kind of can uh, track the action of your group on the input space and on your feature space. So in other words, you can apply your transformation before you apply your data. You input your data into the neural network, or you can input your data into the neural network and apply some corresponding translations there. And the output will be the same, right? So that's one way of thinking about that is that you can
It's
uh,
not the same. It's just going to change in a predictable way, right? Is this
uh,
what?
no. It's the same. If you, yeah. So the idea is that if you apply first your transformation and
G
then
G G.
apply the neural network, yeah, G here, and
Uh-huh.
then there is a corresponding transformation in the, let's say, feature space, right? Then you can apply on your f of x, and the output will be the same, right? So here you put neural network on transformated data. Here you put a neural network on data and then transform that.
Right. So it's not the same. It's you have to transform the output in an appropriate way, which
Yeah,
is
you have to transform, but I mean, yeah, after you transform it's the same. Yeah. And if you set
so equation 2 is when it's the same. Equation 1 is more general.
no, no,
Equation
no,
2
no.
is when
Equation 2 is invariance. Equation 2 is
yes,
invariance.
exactly. So invariance is when the output doesn't change, and this equivariance, I guess, is when it changes with the predictable way
Yes,
described.
yes, 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 yes. Okay. I didn't get your question. Oh, if there was. Okay. Uh,
No, just comment
anyway.
that.
Okay. Yeah. Yeah. Yes. And if your group action is, let's say, your neural network knows that how to mitigate that, to omit that, right? So, for example, if you train your neural network to classify digits, and you have train it on different rotations, and you input rotating images, then the output will be the same. And that's invariant. So your output of your neural network is invariant with respect to the rotation group, right? For example.
But of course, the big question is not how to learn this invariance, but by actually how to impose this invariance. So not that I will teach my network that the shifted images are the same, but I will create the architecture which automatically irrespects.
Yes, so historically that was a plot, right? So before the convolutional neural networks, like the way to do that was to augment your data set and like rotate every image that you have. But after that, it's kind of outperformed in terms of convolution in that. So that was a good guess for neural network, right? And so going back to the paper itself, so we can talk about that, for example, in more specific cases. They talk about mostly 3D cases, uh, but it's not limited to that. Just they somehow motivate this to be like to have a lot of uh, physical examples, right, to test. So, for example, like forces, like I mean, learning gravity. I will talk about that later, of course. Like learning gravity, learning how the translations in chemistry works, and that's also 3D. So they mostly talk about that. And so for their purposes, they have so they consider where you have 3D vector, right? And that's kind of your data point. So for each point in the space, you have the corresponding vector, right? So that's vector flow.
So sorry, Dmitry, I'm missing. Are they proposing to learn the symmetries, or they are proposing a way to actually impose constraints on the network which respects the symmetries? So
They propose a way to impose neural network to respect symmetries. Yeah,
okay,
we'll go.
and then the type of symmetries that they look, what group of symmetries? Is just translation rotations, or there's
Yes. No, no, no. That's actually the interesting point. So the kind I mean, still you have to guess what kind of a uh group symmetry you will need. We will get to that. It's the experimental part, right? But generally, yes. This is kind of uh, I mean, this
so
specific paper again.
let me just
This specific Mhm.
formulate exactly my question, because I mean, I thought about this. So say I tell you exactly the symmetry, permutation symmetry, or shift symmetry. Can they use that to tell me what is the right architecture which respects the symmetry? Or they don't tell you that. They just say, okay, here's an architecture, and that architecture respects that such and such symmetry. So that two different.
The second one, yes, the latter one, because yeah.
So then there can be still other architectures that respect the same symmetries. Okay, fine, but still interesting to see what kind of architectures they use.
Yeah, and again, so the big plot here is that they consider 3D space, and so they mostly talk about that. So, coming from the physics background, there's going to be a lot of familiar words, to say least. Okay, so the data points are these vector fields where you have vectors like from R3, and so they consider it. That's not really important at this point. So they consider different like translation equivariance, right, rotation equivariance, and even more complex cases. So now we also have to talk about okay, so for our group representation, right? So for example, for rotations in 3D space, so how we can let's go back to the equivariance, right? So in the equivariance, we need to predict somehow what transformation we need to do after the input of neural network, right? So to do that, we need some representation of that homomorphism of our group. Okay, so here they represent group elements by Wigner matrices, right? So Wigner matrices, just to remind you, that's so Wigner matrix of power L is a 2L plus 1 by 2L plus 1 matrix, right? So yeah, so here's an example. So for scalar 1, so D of power 0 is matrix 1 by 1, which is scalar function. And for L equals 1, I can see here that that's going to be 2 by 2 matrix. Oh, sorry, no, 3 by 3. 3 by 3 matrix. So that's a rotation in 3D space. Okay. And now going to the main plot, is that how we can represent an action of some. So suppose that we know what kind of a system we have, right? So if we have, for example, some again gravity forces, so we're trying to simulate like planets or something, right? So we can impose some rotational symmetries there. You can say that, okay, it's going to be there, so we're going to use this type of matrices, etc., etc. And so talking about the group representation, right? It's also important to say that there might be different representation, right? So what is a good way to what is a good representation for our group? So for example of this one, let's go back to this block. Okay, so yeah, so with Wigner matrices, again, that's a representation of your action, right? Of your group action. So going back, if you talk about spherical rotations, then you can use your Wigner matrix of power 1, and that's going to be your rotation matrix. Okay, so yeah, here they have definition. So tensor operator F, spherical tensor, is equivariant if it satisfies the identity for all rotations, right? That's the same as definition of equivariance in general form, but here we explicitly show what is the right guess for our transformation, right? So in theory, you can take any group and you can just impose this translation, right? So you need to show what should be here. How should you translate your output of the network to match? The next step with that, with tensor product, we can use this representation, right? So, yeah. So for those who are familiar with quantum physics, or specifically, yeah, quantum physics. So, yeah, so you can represent angular momentum in quantum mechanics, right? With this kind of form, and for your so and when you have two angular momentum, right? So how you can decompose your tensor product is that you can use tensor summation over a direct sum over smaller subspaces, right? So in this example, if you have the product of two vectors, right, 3 by 3, which is usually a tensor product, and which is usually something of dimensionality 9, right? You can decompose that into the smaller representations. So here we can decompose that in a scalar function, vector, and 5-dimensional vector, right? So the total number of components is the same. I mean, so that checks it, right? Okay. So we don't want to work with matrices, and for our tensor products, we will use decomposition in the multiple vectors, right? Okay, and here, talking about the architecture, that's okay. Suppose that we have some trainable layer, which is okay. Here is called V, right? Again, so instead of saying that this is a matrix application, something, we can represent that with a series of scalars, of vectors, etc. Right? So yeah, here's the example on the right. Right. So if we have 2 point masses, right? instead of writing directly product of their relative velocities and um, coordinates, right? We will write them as following, right? So that's just two scalars and then several vectors. Okay. So now we want to, so that's like our data point, right? So we have, let's say, several channels for one point. So it has like mass, has vector, etc. Um, okay, so that's a bit specific example. I will return to that later.
I think we should go to this equations, the most illustrative here, above equation 2. No,
Equation. Oh, yeah,
yeah.
which one?
So
Okay.
the main point of this example is to show that yes, you can perform a rotation of the variable, which is r, transformation of the variable, and then if this variable depends on the tensor, is a function of the tensor, which is here a spherical harmonic, then the components of this spherical harmonic will change in some other way, which is represented by d. And so the point here is that for a certain y, you know how the components will change, and that is going from pure rotation in space to the rotation in the space of this harmonics, which represents different different type of objects. They all transform differently under the rotations. Y0 transforms one way, Y1 transforms in the other way, etc. But the point is that yes, for known symmetries, you know how to go from changing variable, transforming the variable, to transforming the function. Now, you don't know that in general, and that's kind of that's important question. Once I give you a symmetry, and I have a neural network, not just Y, but the actual neural network, that's a function of that. How do I know how this network will transform? And that's the question is about architecture. So hopefully that is the question that they will try to answer, to come up with a neural network that respects the symmetries. Maybe in the physics
Yes.
language, identifying in this neural network, what's a scalar-like quantity with respect to transformations, what is a vector-like quantity with respect to what is a tensor, etc. So that's the big question.
Yes. Yeah. So again, to sum up a bit, right? So the idea is that we want to build something to respect equivariance, right? And for that, we have to know what is a like what is the type of transformation, what is the rule of transformation, right? For our action, for our group action, right? So
We know that. We know that. The group
yes,
is just
and yeah,
yeah.
and here
The
we
question,
know that in this specific example, yeah. Um, so
so if they
again,
answer the question, that they will provide with a maybe not a general architecture, non-linear architecture, but maybe what they want is a tensor architecture, which is not the most general neural architecture, which only involves, linear operations like construction of indices. So if they can do that, that's already would be a step forward.
yeah, yeah, we will go to that. Um, okay, so this is the, yep. Okay, so um, let me go. Yeah, so um, here we can simply say that okay, so the key feature is that if we have some equivariant functions, a combination of them is also equivariant. So, I mean, if f is equivariant with respect to some group action and G is equivariant with respect to some group action, then the combination is also equivariant. That's why we can combine multi-layer structure, right? So we didn't define layer yet, but if we have a equivariant layer, we can combine a series of them, and we have our equivariant neural network. Okay. So here we have their definition for pointwise convolution layer, right? So let's see what it says, right? So it says that how we transform our data, right? So we have our so they call it filter, right? So we would have some kind of filter. Then we have coefficients of our transformations that we computed for our filter, right? So that's a general form. That's not restricting to 3D rotations. In general, we have our transformation rule for our filter. You can think about that as, again, actional group. Yeah. So, okay. I mean, this is just general form. Okay, so they also use something called self-interaction layers, which are just rescaling like pointwise scalars, right? And they even say that it's analogous to one-by-one convolution. And let me remind you that in classical computer vision, one-by-one convolutions, they are used as just a learnable rescale functions that rescales pixels, right? So that's pixel-wise. Okay. Mm, Okay. So now non-linearity comes from the following form. So they have scalar uh, scalar functions, right? Defined as following. And yeah,
I think I'm missing the main idea. I think I'm still missing. I want to see how I give you a symmetry and then you give me the architecture. So I don't.
we will go. Yeah. Okay, let me
And
go to the
and
examples then.
in
Yeah.
the
So
previous talk, in the previous talks, the way some symmetry would be imposed, like augmentation, you said, just making the data set larger. But the question is, can you, given the symmetry, construct a neural network that respects the symmetry, and how? So for now, they're just saying, okay, so you can have this type of symmetry, this type of covariant quantities like scalar vector tensor of that symmetry.
yeah.
That's all fine. That we know. But how you actually construct the neural network, that's missing for now.
Okay. Let's go for their definition of like the diagram of their neural network, right? So mm, here on inputs, you have okay. So going for yeah, because here I didn't explain good enough what channels are, right? So channels is a number. So you can see here red and blue arrows, right? L0 convolution, L1 convolution. That's is exactly what this L says, right? So the L that we defined here, yeah, so the L that we defined here, that's a power of Wigner-Day matrix, right?
Yeah,
So
it will just tell
that's
you about
mhm.
how you transform vectors, how you transform scalars.
Yes,
Uh,
yes, 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 yes.
but that we know.
Uh,
That we know.
okay,
But
I mean, yeah. So to act with our neural network, uh, what we could do is that uh, we compute several convolutions. So we have, if we have two types of convolutions, then we have like L0, L1, then we concatenate them, and that's gonna be kind of our good rate. So mm, now going to the
so, like,
examples.
what
What?
the errors? Maybe, I mean, if they don't have formulas, maybe let's think about what the errors actually represent. What is
Okay, that's a convolution, right? So that's their trainable layer. Um, okay, so trainable in a form that they know exactly how to construct a tensor. Um, where's the definition? Yeah, so they have this definition for a layer,
Yeah,
and when
that's
this, yeah,
complicated. That's too complicated. I
yeah,
think we can explain it simply. You take data, whatever data, and out of data you form scalar, vector, tensor, high order tensors. You can form all those quantities, and the scalars will transform as a scalar, vectors will transform as a. They all be covariant quantities transformed in a predictable way. So that's what this first layer means. But then you're saying, okay, so now, but to evolve a scalar, I'll use a vector. Okay, so vector with respect to the transformation. Uh, um, now that's not going to be a scalar anymore. So if you want scalar to, if you are not contracting any indices and you just follow this blue line in the second layer, hitting the red line, the result of this will not be a scalar, because now it will actually depend on the coordinate system. So so you need to act on the scalar, you need to use scalars to act on the vector. At least in the well, all this is only linear. There's no nonlinear stuff here, because if you wanted to have something nonlinear, then you have to only take nonlinear. You can only take nonlinear maps of scalars, because they will also produce scalars. So even this picture, I mean, the first layer makes sense. You just take your data and you
uh-huh.
form out of them invariant
Yeah, and then,
quantities. But the second layer doesn't make sense, because what is the blue line going from vector to scalars? What does That's not going to be
yeah,
covariant.
actually, that also confused me, and so
That's
they also use several convolutions on the lower one, right? So,
Yeah, so all this is not going to be covariant. Well, I mean, again, what we had before is just general descriptions of the type of quantities that present under the group transformations. So that all we know. It's nice that they had illustrations of how vectors transform and stuff, how the rotations work on the transformations of vectors and tensors. But this is already a neural network. And in this neural network, if your blue line goes, unless by the blue line going back to the red layer, unless that means that I take my vectors, and out of them I form scalars, and then I hit not just scalars, then if that's their definition, then that makes sense. Maybe that's what they mean. At least in the very last layer, layer number 3, the only scalars present, right? So maybe that's what you should actually. The blue line isn't just linear passing of variables, which are higher order tensors, but first contracting them, making out of them invariants, scalars, and then going there. So if that's the case, then of course this is trivially.
I mean, each arrow produces some tensor. If if that's what you're asking about.
No, it cannot be producing a tensor. If you want the if it is again, it can there can be many variables in corresponding to the red line, but each of those variables has to be a scalar. That's the only way for you to know that it is invariant under the transformation. Okay. If it's a vector, then yeah, it's okay. You can evolve it as a vector. You keep it as a vector. It evolves in a vector. You train it as a vector. But then at the end of the day, you have to contract indices of this vector to form a scalar quantity. And that's not obscured here. So one way to guarantee that you're going to have something invariant is to have work only with scalars, right? You input scalars, you form nonlinear functions of scalars. They are also scalars, and you output scalars. That's guaranteed. But I think what they want to do here is to not only transform and evolve through the network scalars, but also evolve higher rank tensors. And we don't need to go to any complications to come up with one non-trivial higher rank tensor. It's a vector. So like, all they had to do is to have an example where you have on the input scalar and a vector, and then show exactly how you are going to construct the architecture such that the result output of this network is a scalar. Has to be a scalar, or otherwise maybe very complicated scalar. It can be, function of different contractions of vectors, but at the end of the day, a nonlinear function of scalar that you can do. What you cannot do is take a vector, pass it through the nonlinear function, then pretend that it's a vector and then contract it. That's not gonna work, because in this case, this nonlinearity of the transformations will make vector not vector. So you cannot just nonlinearly transform vector and then contract its indices. That's not gonna be invariant. So I think that's that's missing. That's missing, and this architecture doesn't capture that. That doesn't, or at least what I understood by the red and blue lines. Because I mean, if you're saying that L equals 0, L equals 1, I hope it's small l from above, not the large L, or maybe there was a small l above that kind of
Yes, there was
define.
yeah, that's a small one. I mean, that's the
Yeah,
like
it's a small L,
retreats
then
scalars, retreats. Yeah.
yeah. So we don't have I mean, we had this, you have particles moving in a box, right? They carry scalar quantities with them. For example, their energy or kinetic energy. If it's a gravitational interaction, we have potential energy. Those are scalars. And those will correspond to L equals 0. They transform as scalars. And then you have velocities of those particles. Now they don't transform as scalars, they transform as vectors. And it's okay for you to pass them any way you like, but it's not okay to take nonlinear functions of them. And
Okay.
yeah.
Just regarding this one, I remember. Okay, there should be another scheme here. Let me just find it. Okay.
Mhm.
Oh, yeah. Guess this is this one.
Mhm.
So, that's how they treat these channels, right? So,
So
um,
three, sometimes three. So three, I assume it means for the dimensions. So if the vector is v times 3, I assume this represents actually velocities. And if it represents
uh,
velocities, I mean, you cannot apply nonlinear transformation and then form scalars out of that. That will not be invariant. So
yes, but I believe that they have
the whole idea
okay,
of
they
our
actually have non-linearities here, right?
yeah, then it's not gonna work.
Before,
Then it's not gonna work. I mean, the whole idea of our paper with this autonomous particles was, okay, it's okay for you to train, agents on the on the only invariant quantities, on only scalars. And if you start passing invariant quantities like vectors, then you better contract them with other vectors. So for example, you have a self-driving car, it has its own velocity, and then the other cars have their velocity. So you can find dot product between the two velocities. That's a scalar. So that you can pass in the input. Now anything non-scalar you just cannot pass in non-invariant. You cannot pass it if you hope to impose the symmetry. Now, if you say, okay, I'm not going to impose the symmetry, I'll let the system discover it. Then, of course, all bets are off. You do whatever you want, and then you just hope that the system will learn that that is a vector and that it has to transform in a certain way. So that's why I mean, it's either trivial what they're saying that you only have to pass scalars, then I agree with this, or something non-trivial, they're saying that there is a way to pass non-linearly vectors and tensors. And then I just don't see how that happens because vectors are
Okay,
not.
yeah, I also don't. I mean, as far as I did think about that, they have nonlinear and then
Yeah,
interactions between scalar and vectors.
then it's not invariant. Then you can just forget about it. No, hold on. They can be
Okay,
interactions.
but yeah,
Interactions
but
can be scalar quantities. It's like you write Lagrangian. You don't write in the Lagrangian, here is a vector plus a scalar. It makes no sense. You have a scalar plus scalar because Lagrangian is a scalar.
okay, but maybe okay. I'm actually not sure. Maybe it has. I don't remember they discussed that.
Because the rest is just illustration that there are different type of quantities that can transform on the different. Yeah, and we know that. So we don't have to actually go to quantum mechanics to see that. We
Okay,
know.
okay, but from their definition of nonlinearity, they have it to be covariant. They say that.
Well, the only way to make non-linear transformation covariant if the non-linearity is applied to scalar quantity. For example, vector
No,
times vector.
of course, that's a scalar transform. Yeah, that's a scalar
So
transform, of course.
it's non-linearity only applied to scalars, and then the rest is irrelevant. It's only scalar, and at the end of the day, this whole thing is just the functions of scalars, non-linear functions of scalars. Then I'm fine with it. Then this is obviously going to be invariant. Yeah. So anyways, but I mean that's the best I can get from the picture illustrations. Now from the formulas, of course we want more than that. We want to actually have a way to input and output covariant quantities. Now and that's the question, how to do that. Not invariant quantities, but covariant quantities. Non-linear covariant quantities. Basically, for example, I input a vector, I do some nonlinear transformation of the vector, and the output is also a vector. But if this is just involves first forming scalar out of vector, and then multiplying this scalar by the vector, well, then that's trivial. And again, you just go, your actual nonlinear neural network is just a function, a nonlinear function of scalars. So again, but there might be something that I'm missing, but I wasn't able to see. So have they tried to actually, trying
Yeah,
into
yes. So
maybe
regarding
maybe
experiments, what
numeric
they
physics?
have,
Yeah.
uh, actually, is that there's quite a big libraries that they use. I mean, the group they developed. So it was, to be honest, kind of hard to get around this because, I mean, if you look in their GitHub with their code specifically for this paper, it just refers and reuses something from their library. So it was kind of hard to understand at first. Um, okay, so as for experiments, so the first one is just rotations. So That's rotation equivariance. So they say that's network type 0 to 0. So they use just one channel, right? Okay. Yeah, so they say that, so the task is that if you have some shapes and you identify this one, then you can rotate them and still perform on augmented data set. Okay. Okay, they don't have a picture for this network, but they say that they use, so okay, they can include several models like channels with L0, L1, but for this task they use just L equals 0, this scalar one, and sum over the sum over pitch vectors of all points. So that's kind
So
of network.
what does it even mean 0 to 1 network? So what does you input scalar, output vector?
No. Oh, okay, yes.
Oh, 0
Here,
to 1,
0
not
to 0,
not this one.
0 to 1. Okay,
Yeah.
0 to
What is
1.
it?
Yes, so now they say that uh, they want to calculate vectors, right?
You cannot
Yeah,
you cannot form a vector out of scalars. So I don't even know what 0 to 1 means.
I mean, you train your neural network to output the vector depending on the scalar.
You cannot do that. That you cannot do.
What? What?
Because the scalar function has no information about coordinate system, it cannot output a vector.
Again, you can construct function that's okay. You can construct neural network that makes a vector out based on the scalar function.
It's not going to be a vector. So you will make a transformation of your coordinate system. Input doesn't change. If input doesn't change, the output doesn't change, and so it's not vector is not going to transform as a vector.
Okay. You're saying that it's not a vector.
It's just impossible. It's
I mean, okay. Here,
you
I
cannot.
guess
There's no free
just
bread, free lunch, whatever.
let me think about that.
So
I
Yaroslav,
guess
I
here
think
it
maybe
just means that they have the scalar as distinct the scalar function. Okay, it's not like they are in the same coordinate system, and from distinct scalar function you can get some vector function which is transforms as vector, but it's in the frame. So they have kind of different frames. It's not like you have the
if it,
scalar function and vector function the same
something
one.
is called a vector, something is called a vector if it transforms as a vector. We know
Yes,
how the
but
vector transforms.
I mean, with respect to what? Not with respect to the scalar function. That's what
With
I'm trying to
respect to the
say.
transformation. So you have a space. In this space, you have vectors. Out of vectors, you form a scalar. You input the scalar to your neural network, and then you want to output.
That's what I'm trying to say. That you don't input. So that's the scalar field. It's not the same as vector
Not a
field.
field, not a field. There's no field, just a scalar, not a field. You have a scalar. There's no way the scalar contains information about vectors. It only contains information about scalars. So, and also it cannot output.
There's no. That's at least I'm seeing that as it's not that you get your scalar from your vector field.
You
So
output three
they're
numbers.
not they're not
You
coupled at any point. I mean, it's just some scalars. It's just some vectors. So and they are in a different spaces. Okay?
doesn't matter in which spaces. You call something a scalar if it's invariant, and a vector is transforms as a vector. Or you shouldn't call them. Okay, so maybe what you're saying that you have one scalar and then it outputs three scalars. Yes, that's possible. And both of
Uh,
then both of them are just scalars. Both input and output scalars. So that's anyways. I wanted maybe Yaroslav can jump in and tell us. Were we able to come up with a neural network, non-trivial network that actually takes input like vectors and outputs vectors, or was
Not
it
really.
always?
Not
Yeah,
really,
I don't think it's possible. Yeah, I don't think it's possible. You can only trivially, yes, you can take a vector that multiply by a scalar. That's another vector. But non-trivially, I just don't see that's happening. But again, maybe their definition of what they mean vectors and tensors here is different, and what they mean by network is different. But you understand, Dmitry, right? You cannot start with a
Yeah,
scalar.
now I understand what you're saying. Yeah.
You cannot put scalar in a function, which is has 3 output functions, one to many. Fine, and then that quantity you call vector. It's not a vector, it's just 3
Yeah, to
scalars.
be honest, to this point, I thought that, okay, they put something like 3 scalars, well, like 5 scalars or whatever. But
That you can do.
yeah,
But don't
that
call
you
them.
can do, but then it kind of makes like senseless to build something called equivariant if you don't actually use it. I mean, yeah, now I'm kind of confused. Uh,
Now, at the level of tensor networks, we actually know how to build, by contracting of indices. We can always, start with many tensors of different orders. You can start contracting indices, and then at the end of the time, and the end of this whole thing, end up with a function which has with a tensor which has only one free index. Okay, yes, that's going to be a vector. But that's whole trivial constructions. It's completely linear construction. There's no nonlinear functions, nothing. Now, what you can do also, inside of this expression, you can multiply it by a function of a scalar. Well, less trivial, but it will still be a trivial network where nonlinearity comes only from scalars. So yeah, I mean, it would be nice to see something like this, but I still don't think that's a general problem how to construct such things. But I don't think maybe it's possible to prove that this is impossible. But anyways, okay. At least we know what they did. So is there any interesting maybe plots or something that they?
oh yes, it was not really that. Okay, there
Oh,
was just a lost
no.
function. Yeah,
Yeah.
they
Oh,
showed.
what they're trying
Yeah.
to do is certainly make sense in terms of formulating the problem, but actually writing down a network that has respect, even approximately respecting the symmetries, is I think scalars is all you can do. Maybe it can be just proved, and then we can put this issue to rest. Oh, anyways, good. So that's it, right, Dmitry? That's all.
Yes,
Yes. Good.
So,
Other
I mean, again, I encourage everyone to check their like library and blog because
sure. Maybe
maybe
there's
you
something
can,
that we're missing.
yeah, maybe there's something more. Yeah.
Diego, you have a question? No.
I almost had a bunch of times, but no.
You had a question, but the question disappeared.
Yeah, basically, yeah.
Uh,
I can see how they go from scalar to vector in the sense that you feed a bunch of points, let's say a distribution of particles, and then you can get like a density or like a few
Yeah.
vectors from that.
yes. But
I think that's what they're trying to say, but
but you put vectors in density. First of all, is going to be a scalar quantity. Okay, so
Right.
then if you want to put something like average velocity, it's a vector quantity. But to calculate the average velocity, you have to input individual velocities. So you input vectors, you get out a vector. Okay,
Yeah.
that makes sense. But you cannot start with scalar and get a vector. It's like, well, okay. I mean, you need it, or you need a preferred coordinate system. So, for example, the observer is moving with such and such velocity in such and such direction. You don't need velocity, just direction as constant, or just oriented in a certain way. The apparatus is oriented in a certain way, and with respect to the apparatus, it measures such and such components of velocities of particles. Well, yeah. Well, then there is a preferred coordinate system. That coordinate system allows you to measure, and that's what could be an input. But you cannot start now. Can you start with a vector and output a tensor? Well, yeah, because you can take two vectors and then form tensor product of the vectors, and that would be a tensor. And in fact, once you have a vector, you're in business. You can form tensors of arbitrary high order. Of course, they are all going to be trivial tensor products of that vector you started with, which again is described by the trivial tensor network and multiplications, maybe by scalars, things like that. But without a vector, there's no way to get a vector or a tensor. Right?
Maybe Diego meant that we can try to form gradients of some scalar field. So if we have some values of scalar in the neighborhood, then maybe we can.
Oh, okay.
Yeah,
well, but
differentiating, right? Yeah,
good,
maybe something
good,
like that.
Good, but then we kind of have relative locations of many objects, right? So and the relative
Vectors
location.
are gonna show up in somewhere in the first layer.
Exactly.
Yeah. Oh, okay.
So
Yeah.
there's no free lunch, in this sense. You have to you need a coordinate system to get vectors. But the problem in general is very interesting. I think it's a more general problem. A given data set doesn't have to do with this. The given data set, and even if you have known symmetries to the data set, how to impose constraints on the architecture, what kind of architectures would or would not be allowed. That's interesting. Okay, very good. Dmitry, are there any other questions, comments? All right, then I'll see you next week. Thanks everyone for coming. Thank you, Dmitry, for the presentation.
Thank you. Yeah.
Bye-bye.